So anything else? No, we don't. I don't see anything else that we should be seeing. Okay, then we have to draw our last view. So now the last view we're going to look at is we are going to look on the XZ plane. Okay, so we're going to view from the. So now we're going to view the Z, and this is X. Okay. So how this will look like is you're going to have, again, this is just a sketch. No, you're going to see this, okay? And then you're going to see this. And then, but all these are in chain line. And this is where we have our element H. And then this is where we draw our centroid, right? So we do have a load going in this direction at 4996. And we have a force that's going down, which is 12002 Newton, right? So we know that if we were to draw the deformation pattern, the deformation pattern will look like this, right? Due to the 4996, right? But the centroid is still a dot. So when that's the case, if I'm going to do this, so right hand rule, rotation about y. So now this is a Ty, which is a torque. Right? So Ty is equal to force multiplied by the perpendicular distance to the centroid, which is 0.15. So we know that the distance from here to here right, 0.15. So this will be equal to 4996 multiplied by 0.15. Okay. So 4996 749.4 Newton meter, right? And the formula we're going to apply is Ty over J multiplied by the radius. Okay. So we know that element H for this case for shear will not be equal to 0. Okay. So anything else we miss out? There's a VZ we know, and the 1212002 is going to induce a axial load. Okay. So there you go. All right. So again, breaking down into views, okay, you can more or less visualize relative to the centroid, whether is it a moment or a torque, and if the force is parallel to the centroid, you take the moment between the force, the distance between the force and the centroid. If the applied force is perpendicular to the centroid, you take the distance from the force to the element. Okay, so these are important points. Anyone, any questions up to now? I know that this is it's not difficult. It's something that you have seen before, but you have seen it the first time. And as I say, we combine whatever we learned from week 1 until week 9 to do something week 10. And then on top of that, we have to later go into Mohs circle. Okay. Right. If no one have question, now I'm going to do one of the most complex problem. Okay, on given in the textbook, and this is where it makes matter more challenging, because now not only we need to know whether is it a force, axial force, torque, moment, shear force, we also have to be able to apply thin wall analysis. Okay, bending moment is the easy part. It's a thin wall analysis that is quite a challenge. Okay, not that you have not learned before. Okay, so let's look at this problem now. And I have to get all this. Go on. Let me. So this is a example number 4. You can see for yourself already. We don't do easy problems in this course. Okay. Then we have to get this information. Then we have, I need this figure over here. Right. So given to us, 4 forces are applied to W200 times 41.6 row beam as shown. Determine the principal stresses and maximum stresses at point A. Okay, so don't worry about principal stresses and maximum stresses first, but rather we want to determine the stress components at A. Okay, we also can do B. Okay, you can see where A is. Okay, so if you look at the transformation that's given to us, okay, so I'm going to follow what is given. Okay, so this will be our X, right? This will be our Y, and then if you use right hand rule, you know that this will be your Z. Okay, so now it changes slightly. The good news about this problem is the geometrical information are all given. Okay, so we are using this information over here. Let me move this across. So we are given this information over here. Okay, we are given that we are going to use this one, 41.7530. Okay, so this is the beam that we're going to use. Okay, so first thing we're going to do, okay, is we are going to identify, like what we have done before. We are going to identify and we're going to identify the axial force, bending moment, torque, and shear force. Okay, we are going to find all this. So the general formula. So usually what we tend to do is we write out the general formula. Okay, so we know that the normal stress we can find is in the Z direction. Why Z direction? Because this is the Z direction over here. So we know that we're going to have PZ over A plus by my over Iyy multiplied by x plus by mx over Ixx multiplied by y. In the shear, we don't know what is it yet, okay, in the shear. I mean, I don't know xy or xz, we don't know yet. But we know that if there's a torque, it's going to be in the x direction. Oh, sorry, it's going to be the z direction. Why z direction? The torque is in the z direction because if I were to draw the centroid, okay, I'm going to sketch the centroid in green now. Okay, for this structure, the centroid will be here. Okay, that is where the centroid is. Okay, so we know that it will be torque in the z direction over J multiplied by C, which is the furthest distance away the centroid. But don't worry, because I don't think when you all were doing 2P04, Dr. Koshi did teach torque in a square section. So as you can see, there will be zero torque. Okay, so not to worry. But we know that there's going to be a plus Vy over Ixx Qx over T plus by Vx over Iyy Qy over T. Okay, so these are the formulas that we're going to. So the first thing we have to find is we have to find our mz, my, mx, tx, tz, vy, vz. Okay, so first thing we're going to do, we are going to identify these forces, the magnitude of these moments, axial load, torque, okay, vy and vz. Okay, good news is we know what is our Ixx, Iyy, right? We know what is our area. Okay, so let's write what we know also. Okay, so from here we know that our Ixx, or from the table, we know that Ixx is equal to 40.8 times 10 to the power minus 6 meter 4. We know our Iyy is equal to 9.03 times 10 to the power minus 6 meter 4. And we also know our area, which is equal to 5320 times 10 to the power minus 6 meter squared. Okay, so we know this, we know this, we know this. Okay, we also know that torque in the z direction is equal to 0. We know this, so this you can ignore it. Okay, so we know our Vyy. Okay, so again, we have to find our yellows. Then later on, the next difficulty part is to find our Qz and Qy. Right? Remember I told you, first moment of area is always the troublesome one. All right. So let's look at this structure. Okay, so we're going to I'm going to sketch this out. Okay, so we know that this is our x, this is our y, and over here this is our z. Okay, so I'm going to first draw our yz plane. Okay, so I'm going to go over here. Now, an important thing to deal with this is you have to be really organized. Okay, if you're not organized, you can't solve problems like this. Okay, This is Y. This is Z. Rotation and X. Okay.